Section 4.5 is going to be graphing sine and cosine functions, so let's go ahead and jump right in. So I'm going to treat this just like I did first semester with transformations. So I want to write this in our form. So I'm going to go ahead and factor out whatever is in front of that x. In this case, it's just a 1. So let's go ahead and pull that out. After I've taken that out, which really doesn't do anything, I'm going to go ahead and identify what the mother function is here. So it's just like first semester. I want to take out everything that isn't part of the original function. So all the transformations got to go. All the stretching, reflecting, compressing, everything's got to go. If I take a look, all I have left is that sine function right there. So I know that that is going to be my parent function. So you guys are kind of used to this by now. I'm a big fan of a whole bunch of little pictures. So I don't memorize, which I know my students here, but I basically trick my brain into memorizing something without feeling like it's doing it. I know what the sine function looks like, just in general, so I'm going to go ahead and draw just a little tiny picture of the sine function. And the only thing I remember is that it stretches up to 1 and down to -1, and then it goes in pi over 2 increments. That's what I remember. So with my little sketch, it should help me get an idea of what my mother points are. So I just take a little tiny sine function. I know that's what it looks like. This gives me an idea, though, of how to find the points that I'm looking for. And I'll show you what I mean. So let's go ahead and set up our XY table here. There are going to be 5 points. All right, looking at my graph, starting at the very beginning, the first point I'm going to see right there is at the origin. That point 0, 0 is on the graph. So 0, 0 is going to be my first point. Now, like I said, I'm going to go in pi over 2 increments. Pi over 2 is going to be halfway. So between that x-intercept that I just used and the next x-intercept, there's going to be one more point in between, and that's going to be my pi over 2 increment. If I take a look at the graph, it goes as high as 1, so the highest point that it's going to achieve. Then I go one more pi over 2. Now I hit the x-axis. That's going to give me pi, because pi over 2 plus pi over 2 is going to be pi. And that gives me back on the x-axis, like I said, so I have another 0. Go back to my graph, go another pi over 2 increment. Now if I add pi over 2 to this, that gives me 3 pi over 2. But you'll notice, based off of my little tiny sketch, that I'm down now at the lowest point, which is going to give me -1. I can go one more pi over 2, and that should get me to the end. If I add one more pi over 2 to this, I'm going to get 2 pi. And 2 pi, that's going to give me 0. That's how I remember the points for sine. I draw a little tiny graph, or I visualize the little graph and go, oh yeah, okay, that's where the points are. I don't necessarily memorize them per se. All right, so now let's jump in. I did the exact same thing that we did first semester, so I'm going to do the multiplication and the division aspects first. So if I take a look at this, it looks like my x's are going to get divided by 1, and my y's are going to get times by 2. So those two values are the ones that I'm going to do first. So I'm going to go ahead and pause right now and fill in the table. Since this is just like first semester, it gets you some more practice back into transformations. So I'd pause, see if we match. Okay, so here's my next table. I went through and divided by 1 to all my x's, which means I didn't do anything. And then I times all of my y's by 2. When I'm doing this timesing by 2, what I'm actually affecting is the amplitude of the graph. Amplitude basically measures half the distance between the highest and lowest point. So it's basically going to talk to us about that stretch, that vertical stretch, or vertical compress, actually, either way. All right, I'm going to go through and do the next thing that I would normally do, which, just like first semester, would go through and affect the add and subtract part. So in this case, it looks like the only thing that's going to be affected are the x's. So it looks like a minus pi. You and I both know you do the opposite, so we're going to add pi. So again, I'm going to go ahead and pause and see if we match. Okay, so here's my final table, and it shows all of my transformations that have happened. One of the things that I have a tendency to do, because I think it makes the graphing a little bit easier, maybe not so much with this one because the x's are pretty easy. When I go through and I see a whole bunch of different denominators, I go through and make them all match, just so that on my graph, because I don't have to simplify on the graph, on my graph I can just go through and count 1, 2, 3, 4. I don't have to worry about, well, where's pi over 6 in comparison to 5 pi over 3? So I get them all to be a common denominator. So what I would do at this point, personally, Again, maybe not so much on this one because it's not all that complicated with pi over 2's. So I'd go through and get everything to be a common denominator, so I can just count. Plus, it allows me to see if I've made any mistakes. What you should see is a nice consistent distance between each of your x's. So here's what I mean. If I take a look back at this table where my orange values are, I'm going to go ahead and write in black off to the side. Notice that looking at all of these denominators, I have a denominator of just in the x column. I have a denominator of 2 and a denominator of 1 because there's nothing there. So the least common denominator would be 2. So I'm going to go ahead and rewrite everything so that it has a denominator of 2 in the x column. All right, so let's take a look at this pi. Well, if I rewrote pi so that it had a denominator of 2, this would be 2 pi over 2. Just write it off to the side. 3 pi over 2 already has it. If I rewrote 2 pi, that would be 4 pi over 2. 5 pi over 2 already has it, and then 3 pi is going to be 6 pi over 2. I'm just rewriting them with the common denominator of 2. Now what I'm going to do is I'm going to compare these to the other ones. So I'm going to go ahead back and just rewrite all of these in black so we can see them. So 3 pi over 2 is just going to come over. So is 5 pi over 2. Here's what I mean by checking. If you take a look at the x's now, all of the ones that I wrote in black, they all have the same distance between them. They should. They absolutely should. If they don't, you made a mistake somewhere. With sine, this is a periodic graph, which means it's got this nice continuous pattern to it. All of the x's need to be the same distance apart based off of the mother points that we used. And if you take a look at this, from 2 pi over 2 to 3 pi over 2 is 1 pi over 2. From 3 to 4 is 1 pi over 2. 4 to 5, 1 pi over 2. 5 to 6, 1 pi over 2. You should have this nice consistent distance. So your graph doesn't look wonky when you graph it. It should have this nice smooth pattern to it. Okay, so I'm going to use those on my graph to go ahead and graph this thing. So up to the side, I'm going to set up my graph. And again, I only make it as large as I absolutely need it to be. So, and if I have extra, I'll just erase it. Notice that the first x value I have is 2 pi over 2, which means I don't really need any negatives. So I'm just going to make a little tiny section over there. Now, the beauty with being able to change the increments on your graph is that you can start anywhere you want, just as long as if it's positive, you're on the positive side, negative on the negative side. But you have to label no matter what. Because you are changing the increments from 1, 2, 3, 4, you have to make it perfectly clear. So be careful with that. So in this case, I'm going to go ahead and just count each one of these boxes as 1 pi over 2. So that would be 1 pi over 2, but I'm not going to use it, so I'm not going to label it. I am going to use 2 pi over 2, though. I'll use 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2. I try to avoid, when I start my graph, going any further than I absolutely have to. You'll notice that I labeled the beginning and the end. I didn't label the first pi over 2 because I'm not going to use it. So now, I'll go ahead and plot my points. So it looks like I need to label my y-axis also. So there's 1 and there's 2. Notice I'm not using the 1, but I am using the 2, so I'm going to go ahead and label that. And then there's the negative 2. So let's go ahead and graph this thing, see what we get. All right, connect the dots. You want to make sure that it's a nice smooth curve. And remember, there's another thing that's helpful. If you take a look back at the first little picture, it should look something like that. So there is one period of this graph, just one. All right, now this thing goes on forever and ever and ever in both directions. If you so choose to, you can put little arrows on the end, that's fine. I normally don't. I understand this thing goes on forever, but I'm just looking at this one period of it. All right, now that I have my graph in front of me, what I need to do is identify the entire laundry list of things that were asked of me. So I'll go back up to my equation. I'm just going to go ahead and rewrite it off to the side again. So up at the very top, rewrite it in hour form when we had it all factored out. And if I take a look at this, when I'm talking about the amplitude, period, phase shift, vertical shift, all of that business, I'm really just talking about the transformational aspect of it, like what I did first semester. So in this case, if I take a look at the number in the front, this 2, that affects the vertical stretch and compress. When we're talking about sine and cosine graphs, the vertical stretch and compress we're referring to as the amplitude. So I would say, getting myself set up over here, that the amplitude is 2. Now, keep in mind, the amplitude will never be negative. Amplitude represents a distance. This 2 represents half the distance from the lowest point on the graph to the highest point on the graph. So if you take a look back at the graph, it goes as low as -2 and as high as +2. The distance between -2 and +2 is 4. Half that distance is the amplitude, which is 2. All right, moving on. I'm going to skip the sine part of it because that's actual function. This 1 in front, that affects the horizontal stretch and compress. When we're talking about the horizontal stretch and compress, we're basically asking how long the period is. Well, the period of a regular sine graph is 2 pi. Because I didn't do anything to it, I had this divided by 1, the period's still going to be 2 pi. How else can you tell? Take a look at your graph. The first point you plotted, the x, is 2 pi over 2. The last point you plotted was 6 pi over 2. The distance between 6 pi over 2 and 2 pi over 2, that's the period. So from 2 pi over 2 to 6 pi over 2 is 4 pi over 2. 4 pi over 2 is 2 pi. So our period is going to be 2 pi. Now, if we take a look inside at what happened to the x, instead of saying we're going to go right and left, we just use a fancy word called phase. So when we're talking about the phase shift, we're still just talking about how much did it move right and left. And in this case, still the opposite of what you see. The phase shift is going to be right pi. Which is why if you take a look at the graph and you compare it to the original started at 0, 0. This one starts at 2 pi over 2, which is just pi. All right, what else do we still have? Domain and range. All right, this thing is going to go on forever and ever and ever. So the domain for this thing, although this one period goes from 2 pi over 2 to 6 pi over 2, this thing goes on forever. So the domain's going to be all real numbers. Okay, my range. Take a look at the graph. This thing is nice and predictable. What you see in this one period is what you're going to get the entire time. It's never going to go higher than it is right now, and it's never going to go lower than it is right now. So our range is going to be from -2 to +2. Brackets on those because it does exist at those points. All right. When we take a look at this, we need to do Y-intercept. That one shouldn't be too bad. And we also need to do even, odd, neither. So what I'm going to do for this one, so I'm just going to go backwards. So let's go ahead and color this a little bit different. Now, the red that I'm going to do, I don't have to do. I'm doing it because I think it makes it easier. So because this thing is nice and continuous, I'm just going to go ahead and continue in the same fashion. So starting at the 2 pi over 2, this would have to go down now, and then come up, and then go up further, and then come down again. So this would just be a continuation of this curve I have in front of me. Why do I find this helpful? Because I can see the y-intercept right now. I can also see that it's even, odd, neither, so which one of those it is. All right, so going back to my black pen here, the y-intercept looks like it's just going to be 0, 0, so that's where it hits the y-axis. And I'll show you another way to do this as well, just by plugging in 0. So y-intercept is going to be 0, 0. Even, odd, neither. Now remember, even, odd, neither. You want to take a look at symmetry. So if I fold this on top of the y-axis, does it sit on top of itself? Nope, definitely doesn't. Does it have symmetry through the origin? So everything in the bottom right-hand corner is going to match up in the top left-hand corner. Yes, actually it is. This point down here and this point up here have perfect symmetry through the origin. So do all of the little dotted points in between those. So I would say that this is odd. So even, odd, neither. this is an odd function. Remember from first semester, we saw a lot of stuff that was neither. We're going to have that as well, too. It just so happens that this one is definitely going to be odd. Oh, asymptotes. There are no asymptotes with sine or cosine. Those are the only two that don't have asymptotes, though. So everybody else is going to have asymptotes except for sine and cosine. So for asymptotes, I would put none. And there we have our first sine graph. All right, let's flip to the next page and see what we got there. Another sine graph. All right, so I'm going to go through the same process again here, but I'm going to do a lot of pausing, so this is going to go a lot faster. So first thing I'm going to do is I'm going to factor out the 3. So let's go ahead and do that, see what we get. Okay, so I factored out my 3. I double check to make sure that I'm right. If I distribute the 3 inside, I'd get 3 pi over 6 versus pi over 2. All right. Now, you also notice that I put a little -1 in the front so I could see what was actually happening with my y's. Set up the same thing. I have my little tiny graph off to the side. This is still a sine graph, so I have a little sine picture there. It doesn't have to be perfect, just as long as I have an idea of what it is. All right, I'm going to go ahead and pause and set up my mother points. See if you can do the same. So again, I used the same curve along with the sine curve that I did before. So I went in pi over 2 increments. I started in the middle, and then I went up, back to the middle, down, back to the middle. So keep that in mind when I'm going through and doing these points. All right, so take a look at my x's now. Looks like I have to deal with the 3 that I factored out, and I need to deal with my y, so I got to deal with that -1. So I'm going to take my x's and divide them all by 3. I'm also going to take all my y's and times them by -1. So again, I'm going to go ahead and pause. Now would be a good time for you to do so as well. Okay, so I went ahead and set up my table, divided by 3 and then times by -1. Previously, on the previous slide, I said something about how when I got to my graph at the end with my x's, I made all the denominators look the same. I take a look at this, and I'm going to have to subtract a pi over 6 from these. So actually what I'm going to do right now is I'm going to make all the denominators match so that I can easily subtract the pi over 6. So I'm going to make my life just a little bit easier here. So plus it'll go through and match all the denominators anyway. So I'm going to take a quick second and rewrite all of my x's so that I have denominators of pi over 6, except for the 0, because that doesn't necessarily need it. Now I chose pi over 6 not because I'm subtracting pi over 6, but because by looking at the x's I have right here, a common denominator would be 6. So I'm just going to go ahead and rewrite all of them off to the side with their with their 6 denominators. This one already had a 6. I need this one to have a 6. Plus, as I'm going through and doing this, remember, this gives you an opportunity to make sure that all of your x's are the same distance apart, which they are. It looks like they're 1 pi over 6 distance. All right, now I am going to use those x's, not the ones with the different denominators, and I'm going to do the subtracting pi over 6 transformation and the -2. So now would be a good time to pause. You'll notice when I filled in the table with my x's, I did not simplify them. I like that they all have the same denominator because I can see that consistent distance I keep talking about. It looks like these are my final points. Double check to make sure that everything's the same distance apart. Yep, it is. The y's, not so much, but I definitely look at the x's. All right, let's go ahead and graph this thing now. So it looks like I need to go a little bit to the left and mostly down. So set up my graph to match what I need it to be. A bit to the left and mostly down. Actually, all down. Let's see if that'll be enough. All right, it looks like pi over 6's, so I'm going to go by pi over 6's. So there's negative pi over 6. That is my first point, or my first x, so I am going to label it. And then my next one will be 3 pi over 6. So 1, 2, 3. And if you want to use 2 boxes so that your graph looks bigger, that's fine. Just make sure that you label it. That's the important part. And then I need -1. That's one of them. -2 and -3. Okay, looks like I have a whole bunch of extra graph that I don't need. So let's get rid of this. Remember, I am only graphing one period. It's not like this is the entirety of the graph. This is just one period of it. All right, let's go ahead and plot what we got. All right, connect the dots. Nice smooth curve. Oh, looks like there's our sine graph. Okay, so this definitely looks different than my first one. Why? Take a look back at the function. You took all of your y's and you times them by -1, which means you did do a vertical flip or a vertical reflection. So in the beginning for the sine graph, my little picture, looks like I have a bump to begin with. Well, that bump got flipped over, so now the first part of my graph is a dip, which makes sense. All right, we need to identify all of our stuff. And I'm not going to rewrite my equation this time. I'm just going to go ahead and extract information from it. So my amplitude, again, you can take a look at the graph or you can take a look at the equation. The amplitude is going to be half the distance from the max to the min, or the min to the max. So if I take a look at this, from -3 to -1 is 2 units. Half of that, that's 1. So my amplitude is 1. Remember, it's never negative, it's distance. Then we've got the period. Again, you can take a look at the equation or you can take a look at the graph. If I take a look at the graph from -π/6 to 3π/6, that's a 4π/6 distance. 4π/6 is the same as 2π/3. Now, on my graph, I didn't simplify my increments, but on my answers, I must. So make sure that when you identify amplitude, period, phase shift, vertical shift, that they are simplified versions of the numbers. All right, so now we've got phase shift. Well, if I take a look at the graph, I'm going back to the graph this time, normally I would start at 0 on the x-axis, but this time it looks like I'm starting at -π/6. So that means that I went left π/6. And then my vertical shift. Vertical shift can be a little bit harder to see on the graph. So with vertical shift, what you want to do is take a look at that middle line, your equilibrium basically. So I'll color code it. So this little equilibrium line here. Notice that it's down at -2. Basically means that you shifted the entire graph down 2 units. Again, I got all this from the graph, but every single piece of this can actually be extracted from the equation as well. All right, then Y-intercept is staring right at me, so I don't have to do any work for that. Which means when x is 0, looks like my y is -3. If I do my domain, so the beautiful thing about domain is that it's going to be all real numbers for sine and cosine every single time. It's like a free point here for you. Range, remember this is just a snapshot of what the whole thing looks like, so it's going to go as low as -3 and as high as -1. It'll never stretch lower or higher than that for this graph. So there's my range. And then I think the last thing I need is even, odd, neither. Well, if I take a look at this, if I fold it, now I'm already on top of the y-axis, which is why I'm not going to go backwards or forwards for this. It's already sitting there. If I fold on top of the y-axis, these points do match up. This point here would match perfectly with that point, which means I do have symmetry to the y-axis, which means this is even. And then asymptote, another easy point here, none. All right, so there's our second problem. Okay, on to our third slide. Looks like we have a cosine graph now. The process is exactly the same, though. You just need to know what the cosine curve looks like. Again, that's where my little pictures come in. So I'm going to go ahead and do the exact same thing that I've done previously. Go ahead and take out that 3, treating it just like transformations. Do a quick check, make sure that when I distribute the 3 I get back what I started with. Sure do. All right, now I have my little picture for cosine. Cosine this time doesn't start at 0, 0. It actually starts at 0, 1. So it's like I'm partway through a peak. So then it comes down, dips down, goes up. That's what my cosine curve looks like to begin with. So I have that drawn off to the side. I'm going to do the exact same thing that I did before. So let's go ahead and extract the points here. So take out my table. It's going to be 5 points. And I do the exact same thing that I did. So this is the first one I'm going to start out, which is 0. But notice the height is actually up at 1 now. I go a pi over 2 distance, and I'm at 0. I go another pi over 2 distance, and I'm down at -1. I go another pi over 2 distance, and then I go another pi over 2 distance to get myself to the end. Those are going to be my mother points for cosine. And I don't memorize this. I take a look at the picture. So I guess I do, but I use the picture to help myself. Without the picture, I struggle a little bit. All right, so now I'm going to go ahead and do the exact same thing that I did. So I'm going to set up my x's. See if you can figure out what you should be doing with them. Remember, this is transformations from first semester. So why don't you go ahead and, I'm going to pause, fill it in. So why don't you pause now and see if we can match. Just for the x's, then we'll pause again for the y's. Okay, so I went through and divided by 3. Notice that I'm going to take my y's and times them by 1/2. So now at this point, I am going to go through, match all of the denominators for my x's, because I've got 3's and 6's, so my common denominator is going to be 6. Then I'm going to perform the rest of my transformation for both my x's and my y's. So now would be a good time to pause. Remember, you may need to do something to get the x's to work out for yourself by matching denominators. So make it as easy on yourself as possible. So let's pause, see if we match. Okay, so here are my final points. I noticed that I needed to add pi over 3 to all of my pi over 6's. So taking a look at my last table here, what I decided to do is, instead of trying to add pi over 3, I went ahead and just rewrote it as 2 pi over 6. So I gave it the common denominator so that when I added, I could add easily. Plus, I could still see that nice consistent distance between each of the points. So all of my x's are the same distance apart, which is good. And then with my y's, I went ahead and just did what I would normally do. All right, let's go ahead and graph this thing. And can we fit it off to the side? I think so, maybe. All right, let's go ahead and get our graph. It looks like we need to start to the right. I don't need any left. And all down. All right. Okay, 2 pi over 6. So there's 1, don't need that one. Let's do 2 pi over 6. Now I could have just started at 2 pi over 6 if I wanted to. But again, you want the distance to be nice and consistent, so I don't want it to look like some things are closer together and some things are further apart. So I start at 2 and end at 6. 3, 4, 5, 6. I also don't want this to be so tight that I can't get the points in. So I need a -1/2 and a -1 and a -1.5. So I'm actually going to go 2 boxes to represent -1. So there's -1. And there's -2. All right, I know I don't need to label -2, but I do need -1.5. So at least this gives me some sort of bearing for my points. Well, let's go ahead and plot. So 2 pi over 6, I'm at -1/2. 3 pi over 6, -1. And then let's continue on with our points. Oop. Now, when you sketch this, I know it looks like a V, but you want to make sure that it looks like it's coming off a curve at the top. Then it starts doing a little cup in the bottom. So you don't want it to look like this sharp V, because that's not what it looks like. So, looks pretty good in comparison. Actually looks like the original one. Mine was a little bit more exaggerated. And now we should be able to identify everything. So I think I'm going to go back to the equation this time to identify the important information. So, amplitude. Amplitude is going to come directly from the number in front of the cosine. So my amplitude is going to be 1/2. I can see that from the graph, but I can also get it from the equation. Period. My period is going to come from that number. Well, it's not going to be 3. Remember that the period for a regular cosine graph is going to be 2 pi. So what I'm going to do is I'm going to do 2 pi over 3, which I can also see from the graph. Phase shift, well, it was the right and the left movement, so it's that thing inside. Looks like it's going to be right pi over 3. And then my vertical shift is this number here at the end, which is minus, so down 1. All right, so I can get all of that from the graph, or I can get it all from the equation itself. All right, now taking a look at my graph, I can't determine if it's even, odd, neither, or what my y-intercept is. So I'm just going to go ahead and back it up and see how it looks. So again, the beauty of having the increments all the same is you can just kind of go backwards with the points. Just following the pattern. So this would be another period of the graph backwards. I don't need it. I'm using it just to find some more information. If I take a look at this, it looks like my y-intercept is -1.5, which makes sense. So not necessarily from my table, it's not in there, but I can go backwards to find it. So my y-intercept is 0, -1.5. I would say that based off of these points, this is going to be even because I can fold it on the y-axis and it matches up. Asymptotes, just like sine, cosine doesn't have any. And then it looks like I skipped domain and range. So for domain, beautiful, easy points. It's going to be all real numbers. And then for range, remember that what I graphed here in black is exactly what the rest of it looks like. You just basically copy paste it the entire way down. So it goes as low as -1.5 and as high as -0.5. So as low as -1.5 and as high as -0.5. And there's our cosine. Okay, on to our last question for this section. So we've got an application problem here. Now I know that this didn't copy out as well from onto this document, but it's the exact same thing that you guys have in your notes. I just wanted to be able to have the directions in the picture in front of me. So they gave us a sine curve and basically says that it follows this pattern. Awesome. Our job is to be able to find the period, amplitude, and equation for the sine curve. All right, taking a look at the picture itself, let me do some marking on my picture here. Whenever I'm talking about the period of a graph, the period is that the horizontal length it takes for an entire sine curve to be complete. So to see the 0 at the beginning, the bump, come back to the 0, the dip, come back to the 0. So if I take a look at this graph, I have an entire one period of sine. So what I would look at is I would look at from the beginning to the end. That's going to represent one period. So what I do is I take a look at, just going down here to the x-axis, I take a look at how far that was. Now, it looks like the period of this thing is going to be 40. So I would write that down. So it looks like my period is going to be 40, which I'll use in just a minute to help myself with the equation. All right, amplitude. Amplitude is that vertical distance. Now, it's not from min to max, it's from min to max cut in half. So I would look for my lowest point and my highest point. It actually looks like they did it for me, which is kind of nice. So I'm looking at my lowest possible point on the sine curve, which they identified as -65, and then the highest possible point on the sine curve, which they identified as +65. So my job is to find half the distance between those two. Well, from -65 to +65 is going to be 130. 130 cut in half is going to be 65. Or what you can do is you can take a look at that equilibrium. So here's that middle point. The amplitude is going to be from that middle equilibrium where the zeros are located up to the maximum. So that is going to help me with my amplitude. So I know that my amp is going to be 65. All right. Now, I do want to be able to do the equation to this, so I need a couple of things. I need to see if it's been shifted up or down at all, and I need to see if it's been shifted right or left at all. So the up or down part I'm not too concerned about because, I'm going to go ahead and do my color coding here, and looking at that 0 point. So for my vertical shift up and down, I take a look at where this equilibrium line is and what the x value that's there. Now it looks like the x value is 0. Now I know the graph looks kind of funny, but if this x value is at 0, then there is no vertical shift. So this tells me that there is no vertical shift. Now I need to think about phase shift. So take out my color coding again. For my phase shift, I need to look and see if this point that would be 0, 0 has been moved at all, right or left. Well, if I take a look at this point here, I know we're getting it's getting a little crowded here. This point at 0, 0, the question is it still at 0, 0? Well, yeah, it is, because taking a look down here at my x-axis, if I were to go backwards, so 40, 30, 20, 10, then this value would be 0, 0 as well. Which means this value up at my point, or excuse me, that x down there would be 0. This would be 0 as well. So I'm still at 0, 0 technically. So that means that I have no phase shift either. So this tells me no phase shift. All right, now what I need to do, no vertical shift, no phase shift, that makes it a little bit easier. I need to go through and figure out where all this stuff goes in. So I know my regular sine function, go ahead and get myself set up here. It's going to be a times sine b x minus c plus d. All right, so our basic formula here. A is going to be our amplitude. All right, so I can plug the 65 in there. B is supposed to be the period. So if I take a look at this, but my period is supposed to be 2 pi over b. All right, my c and my d, I don't have to plug anything in. So let's see if we can start plugging some stuff in. Okay, so I went ahead and plugged in my 65 for my amplitude. I know that there isn't going to be a C or a D because there was no vertical or no phase shift, but now I have to deal with the whole period being 40. All right, so it's not that the B is the period, it helps you find it. If this is a sine curve, then I know that 2 pi over B is supposed to give me the period. So I'm going to set up a little tiny equation here off to the side. So 2 pi over b is supposed to give me the period. Well, my period, I determined, was 40. So my job now is to solve for b. I have to figure out what value actually is going to get plugged in there. So if I cross multiply and then divide a little bit, this is going to give me b is equal to 2 pi over 40. If I go ahead and simplify that, that's going to give me pi over 20. So my b value that's going to get plugged in is pi over 20. Now what you can do, just to make sure, is you can check. So to check this thing, we can do 2 pi, I know it's going to look hideous, over pi over 20. simplify that. It's going to be 2 pi divided by pi over 20, which is 2 pi times 20 over pi. Pi's cancel. 2 times 20 is 40. There's the period that we wanted. So you don't just plug the 40 in, because that's not going to work. You have to do 2 pi over b to get what the period is going to be for sine and for cosine also. For the other ones, it's a little bit different. All right, so now I have my equation. Now I'm going to use the equation to estimate the change in line of sight velocity on day 36. So all I have to do is plug in 36 for x. That's all this is saying. So I go back up to my equation. 65 sine, that's going to be pi over 20 times 36. Now, the entire lesson, this is the first time I've grabbed my calculator. So I don't need my calculator for anything before this, but for this one, I do. And if I type it in, I get negative 38.2060. And I believe it was meters per second. All right, that's our notes for 4.5.